I hope all of you got the hard copy of the alcohol study pack 10B with you. We are almost at the end of the organic chemistry and end of the syllabus. In fact, there's only one more class, one more lesson. That is mass spectrum and IR after this to complete the syllabus. So I hope you got the rest of the study packs printed so you can write the answers in the study pack itself. Today's lesson is on the alcohols, the chemistry of alcohols, and the reactions of alcohols and the manufacture of alcohols. If you take alcohols, the general formula of alcohol is CnH2n plus 1 OH. That means you replace one or more, generally one hydrogen of alkane with OH. It's a monosubstituted alcohol. Only one hydrogen is substituted with OH. What I have drawn here is the most common alcohol, which is ethanol. So you can notice one of the hydrogens of alkane is substituted. So general formula of alkane we know is CnH2n plus 2, right? So when it comes to alcohol, you remove one hydrogen, make it plus 1, and add a OH instead of that hydrogen. So the first member of the homologous series of alcohols will be a methanol, CH3OH, and then you keep increasing the CH2 groups. You have ethanol, then you got propanol, butanol, and then you got depentanol. This is the homologous series of, this is C5H11 OH, homologous series of the first 5 members of the alcohols, right? So methanol, ethanol, propanol, butanol, pentanol. Please copy these 5 members. The first 5 members of the homologous series of the alcohols. Now when you compare with the alkanes, these alcohols have the polar CO group, the polar CO bond, which makes the alcohol more reactive than alkanes. Now this CO bond of alcohols, in fact it is a polar bond where oxygen is electronegative and carbon is electropositive. So that's the reason these alcohols generally undergo nucleophilic substitution reaction, because the nucleophile is nucleus loving species, can easily attract and attack this carbon and substitute the OH to a halogen. Substitute the OH to a halogen, therefore the alcohols undergo nucleophilic substitution reaction. So alcohol is organic compound that contains carbon bonded to electronegative oxygen, forming the COH bond. The CO bond in alcohols is polar. This makes them more reactive than alkanes, especially with ionic reagents. So please copy this diagram, which shows the bond polarity of the CO bond. So like we classified in the last class, the classification of the haloalkanes as primary haloalkane, secondary and tertiary haloalkane. Similarly, we can classify the alcohols also same way, primary, secondary and tertiary. Why is it important to classify the alcohols into 3 categories is that their chemistry sometimes differs when it comes to the structure. Right, their chemistry sometimes differ when it comes to the structure, right? So to take primary alcohol, the OH attached carbon is directly attached to 2 hydrogens or 3 hydrogens or one single carbon. This is primary alcohol. If OH attached carbon is attached to 2 hydrogens or 3 hydrogens or directly attached to 1 carbon, it is a primary alcohol, right? So in primary alcohols, OH attached carbon directly attached to 1 carbon. That carbon can have any amount of carbon atoms or 2 or 3 hydrogen atoms, just like in haloalkanes. So even this is a primary alcohol. As for the secondary alcohols, OH attached carbon is directly attached to 1 hydrogen or 2 carbon containing groups. 1 hydrogen or 2 carbon containing groups. As for tertiary alcohol, the OH attached carbon is directly attached to no hydrogens or 2 carbon atoms, 3 carbon atoms, and those carbons can be attached to any amount of carbon atoms. Right? Please copy these examples for primary, secondary, and tertiary alcohol. Right? If you are done, those who are finished, you can turn to the next page and name the first few alcohols. There are 4 alcohols given, and those who join late for the class, you can copy these primary, secondary, tertiary structures, and as well as the homologous series, the first 5 members, and this diagram which shows why alcohols are polar. Please copy the first 5 homologous series, and polar molecules show why alcohols are more reactive than alkanes, and then the examples for the primary, secondary, and tertiary alcohols. Others who are finished copying can try naming the alcohols given on the next page. So when you're naming the alcohols or any molecule, first of all, you identify the main carbon chain. There are 3 rules to identify the main carbon chain. That's the longest chain, and it should contain the main functional group and the maximum number of subsidiary groups. The subsidiary groups are the attachments. And after identifying the main carbon chain by applying these 3 rules, you should number the main carbon chain. When numbering the main carbon, there are 3 rules again. In numbering the main carbon chain, there are 3 rules. The first rule is that the functional group attached carbon should get the lowest possible number. If the functional group is a carbon-containing group, then you can give number 1 other than the ketones and esters. And then if the functional group is absent, then the double bond carbon should get the lowest number. If the functional group is absent, double bond carbon should get the lowest number. But if there is no functional group, if there is no double bond, and then the first point of branching should get the lowest number. As for the first molecule, we start numbering from this corner because this is the longest chain. 3, 4, 5. The longest chain contains 5 carbon atoms. That's the longest chain. And there's a methyl group, 1 substituent, the third carbon, and there's an OH group, the functional group, on the 3rd carbon. So we can name this molecule as 3-methyl pent N 3-ol. 3-methyl pent N. N is the middle name. Carbon-carbon single bond. The 3rd carbon has the ol. 3rd carbon has the ol. Not the 5th carbon, Darshan, it's the 3rd carbon which has the ol. And N is important. In the next one, we can number from the left side, because right side, if you number, the functional group attached carbon gets number 2. Number from the left side, the functional group attached carbon gets number 3. So right side is the correct numbering. We can name this as 3,3 dimethyl, that's 2 methyl groups, built in 2-ol. 2nd carbon has the ol. 2nd carbon has the ol. This is pentane, 3-ol. Two-methyl propane, 2-ol. In some skeletal structures, the point where the 2 lines meet and where it ends, there's a carbon. There's a carbon here, there's a carbon here, carbon here, carbon here, and a carbon there. Is it clear? So check the names, please. If you've forgotten how to name them, please refer your Unit 1 Organic Chemistry, the very first unit, 4A. I have given the rules. 4A, towards the halfway through, I have given the rules of naming organic compounds. I have summarized all the rules in 1 page. So go through those. You will be able to get the hang of naming, the rules of naming. As physical properties of the alcohols, they are just like the haloalkanes. As you go down the alcohol homologous series, their boiling and melting points increases. The reason for this can be explained with respect to the strength of the increase in the strength of the dispersion force. Dispersion force, or you can say London forces, because as you go down the homologous series, number of electrons increases, which accounts for the increase in the strength of the intermolecular dispersion London forces. Don't say van der Waals forces, because when you say van der Waals, you are including permanent dipole attractions also. It is true, alcohols being a polar molecule, there is permanent dipole attraction. So intermolecular attraction in alcohols is van der Waals. Why we say van der Waals? Because there's both permanent dipole, and induced dipole attractions in alcohols. But as you go down the homologous series, what increases is not the permanent dipole attraction. What increases in strength is the induced dipole attractions, because number of electrons increases down the homologous series. So that accounts for the increase in boiling and melting points, and that accounts for the decrease in volatility of the alcohols. Alcohols become less volatile as you go down the group, down the homologous series, because as intermolecular force strength increases, it won't be easily volatile, it will be less volatile, right? And the lower members are completely soluble in water, completely miscible in water, whereas high members are less soluble. This can be further explained in terms of the intermolecular attractions and also in terms of hydrophilic, hydrophobic nature. So as you go down the homologous series, the tail part of the molecule is long. The tail part is hydrophobic, and the head is hydrophilic. Why hydrophilic? Because it's polar. This is polar, and the tail is non-polar. Right? So when the hydrophilic part becomes greater in size, water molecules will not be able to come close to this molecule because it repels the water. Such alcohols are immiscible with water. But the shorter members of the homologous series, they can easily form hydrogen bonds with water. That's why methanol, ethanol, propanol, all these alcohols, lower members, they are soluble in water because they can easily form hydrogen bonds with water molecules. That's one explanation. Second, you can say, as you go down the homologous series, alcohol attractions become very strong because dispersion force strength increases. That's a solute-solute attraction. So this is a solvent-solvent attraction. So when you put the solute into solvent, what happens? If it is to make a solution, that means it should form solute-solvent forces. This is where we say it has formed a solution. That means the solute has dissolved in the solvent. For this to happen, the solute-solvent force should be stronger than the solute-solute and solvent-solvent forces. So if the product, the bond which is formed during the product, because we know bond formation is exothermic process, so bond breaking is endothermic process, right? So the energy release when the bond is made, if it is more than the energy of the intermolecular attractions between the solute and solvent, then the solute and solvent bonds will be broken in order to form the strong solute-solvent attractive force. So this is a point where we say the solute has dissolved. If this doesn't happen, it is not soluble. That means solute we put to solvent, solute forces are strong, solvent are strong, then the solute-solvent. The solute will stay as solute, solvent will stay as solvent. It will not dissolve. Right? So that's what happens as you go down the homologous series. Solute-solute attractive force will be much stronger. Therefore, that such alcohol will not dissolve in water.